Adi, you are there, na?
Yes.
Okay. Let's see. So first, this part, it starts with the Lorentz force. Okay. So we're going to learn about what do you mean by Lorentz force. So this force is basically called as Lorentz force because he put forward this theory, So to honor him, they named it as Lorentz force. Now, what is Lorentz force? So let's say out here you have there's a magnetic field line. Let's say there's a magnetic field which is going from this way from north to south. If you remember the magnetic field lines, they'll always travel how? From North Pole to the South Pole. And in between this magnetic field, what we are doing is we are placing a conductor, guys, out here. Okay. So we are going to place a conductor. So let's say here you have a conductor through which we are passing what? Current. So there is a conductor through which we are passing the current. So I'll name these as I. That's the direction of the current. And you can see the magnetic field is what? North to south. So guys, just imagine that right now, like right in front of you, imagine there is a cuboid which is filled with the magnetic field lines. And the magnetic field lines are going this way. They are going from north to south. That's the direction. Remember, they always have to be north to south. If you remember, 9th standard magnetism. And the current is, you know how current is passing through it, like in between the magnetic field lines, like throughout in between of the cuboid, it's like a needle which is passing through it, the direction of the current, or a wire is pierced through it. Now, when you do this kind of a setup now, you know what will you experience? Let's say, for example, you can see there's a pen. Let's say this is a horseshoe. This is a horseshoe magnet, guys, out here like this. So there's a north pole, there's a south pole. So the magnetic field lines are there between them, right? North to south. That's like I have drawn on a paper. Got it? And between these now, I am placing a current carrying conductor, the conductor which was carrying a current. So if you place a conductor in such a magnetic field, it will experience a force. And what will you notice, that your conductor will bounce up. It will jump up like this. Got it now? So whatever the conductor, it will just bounce up. It will go upwards. You'll get a jerk basically. So it's like within the air only you have placed the conductor, but that conductor will get bounced. So it might actually bounce up. It might go down also. We don't know how it will go. That we'll discuss later on. Okay. So now see, so this force which it experienced now, that is called as a Lorentz force. Okay. Now first thing, why did it experience the force? That is because when you pass the current through this wire, what was developed around this wire? Anyone remember? When you pass current, what is developed around the wire? Magnetic field lines, right?
Field.
Yeah. Now, if you notice here, we've got two set of magnetic field lines. There are magnetic field lines around the around the wire. You can see its own magnetic field line. And there are also magnetic field lines which were present, of another magnet, like a horseshoe magnet or any another magnet. So because these two different magnetic field lines are intersecting, or they are colliding, you can say sort of. So what will happen? There will be a resultant force on it. Like when you get two magnets closer, they'll attract or repel. Something like that is happening here also, guys. That conductor will, be pushed up or downwards. Okay. This is also called as motor effect. You don't have that in your portion though, those terms and all, but it's also called as motor effect. Because that's how this concept is used for the working of a motor. Now,
Motor we don't have.
You don't have motor in portion. I'll tell you what is. I'll give you marking also. So guys, see out here now, this is at right angle at 90 degrees right now. Correct. So if the angle formed between them, okay, look at it, guys. If the angle formed between them is equal to 90 degrees, then the conductor will experience what? Maximum force. Okay, when will it experience maximum force? When the angle is 90 degrees or they are normal or perpendicular. They can use the word normal also. And if this angle is 0 degree, when will the angle be 0 degree? If you place a conductor like this, see, or you place a conductor like this. Got it now? Basically, if you place a conductor parallel to the magnetic field lines, the force it will experience will be what, you can say it will experience the minimum force, or rather you can say 0 or negligible, 0. Here, how are you placed it? it is either parallel or it is along the magnetic field line, then there will be a zero force on that conductor. Got it? So this was put forward by scientist Lorentz, and that's why they call it as a Lorentz force. Okay. Now, the force which is experienced by this conductor, na guys, it depends upon three factors. So the factors which affect the on which the force depends is given by the formula BIL, Bill. So to remember, you can remember it as F is equal to Bill, BIL, Bill. Now, if F is equal to Bill, guys, what will be B equal to? Fill. Look at it, isn't it? B is equal to fill, or you say F upon L, however you remember it. Now guys, let's discuss what are these factors now out here. So out here first, let's say this is, if you look at the formula, what can we conclude from here? That force is directly proportional to what? B means what, magnetic field. I'll just tell you first what each of the term means actually. So see, F stands for what? Force out here. B stands for magnetic field, like the strength of the magnetic field. I stands for current. And L stands for the length of the conductor. Now, what is the unit of force? So force is measured in Newton, current is measured in ampere, and length is measured in meter. These are the units. Okay. So from this formula, we conclude that force is directly proportional to magnetic field. Means what? If you use a stronger magnet, okay, if I'm using a stronger magnet, it will experience more force. It will go upward with a greater force or more deflection. It also depends upon the magnitude of current. Again, more the current, more it will experience force. And also directly proportional to length of conductor. More the length, more will be the force. Done. Clear? So guys, these are the factors on which the force will depend. So they can ask you what are the factors on which it depends and how it depends. Now guys, we are going to use this transformation now. We are going to use this formula now to figure out the units of magnetic field. So if you realize now, what is the unit of force? Newton per ampere and per meter. Anybody's got doubt in this, how to identify them? So it's Newton upon ampere upon meter. So Newton per ampere per meter. Okay. Or if you don't like these units, guys, don't worry. You can just write a capital T as a unit. That's a symbol. Okay. You can also write what? Capital T. Got it, everyone? Now, if you're finding it difficult to write capital T, don't worry. You know what you can do? You can just write the full form of T, which is what, Tesla. Okay, it is called as what? Tesla. Now the next car coming up, probably in India also they are launching this now, Tesla. Or there is also another unit which is called as Weber per meter squared. So it's called as Weber per meter squared, not Weber. So it's written as WEBER, Weber per meter squared. Or if you find this difficult, you have another option, guys. You can write WB, named after the scientist Weber per meter squared. So these are the few units. You need to learn all of them because they might give you any one of them in the exam and then ask you to identify them, guys. Clear, everyone? So usually we always prefer to write what? Tesla, that only unit. Or if they ask you SI unit, it will be Newton per ampere per meter. Yes, got it? So these are the factors on which the magnetic field depends. Now, just one last thing that you need to know is what do you mean by Fleming's left-hand rule? So I'll repeat again, guys. You need to just understand what is a Fleming's left-hand rule. You do not actually have any application of this. And definitely one of these will come only in your exam. What is Fleming's left-hand rule? Or there are some more rules. A couple of them they'll ask you. So guys, let's start with this now. What is Fleming's left-hand rule? So the Fleming's left-hand rule is first of all used to identify the direction of the force. Remember I told you the conductor will experience a force. Now in what direction will it experience the force is what we need to learn. So we are going to use Fleming's left hand rule to identify that. Now, so what is Fleming's left hand rule? It states that if you stretch, okay, if you stretch your fingers mutually perpendicular to each other, okay, but I'll tell you which fingers. All of them can't be mutually perpendicular to each other. So if you stretch your forefinger, okay, your center finger and your thumb such that they are mutually perpendicular to each other. So guys, what we do out here, one second. Yeah, so look at this guys. You have to stretch your forefinger, center finger and the thumb such that they are mutually perpendicular to each other. I hope you all can see. Guys, this position, I call it as a yo. So every time we say yo, this is how you get it, guys, your hands. Okay, that is called as the yo position. That is the forefinger, center finger, and the thumb. Now, what does each finger represent now? So forefinger means what, magnetic field. It represents the magnetic field. Center finger represents what? The direction of the current. And thumb represents the direction of the thrust, or in simple words, thrust is also called as what? Force. Guys, I'm actually purposely using the word thrust just so that you have the same initial, so it's easy for you to remember. Look at it. F for fore, F for field, C for center, C for current, T for thumb, T for thrust or force. So we are using this rule for what? Identifying the direction of the force. So what you have to do, you have to first go to your position and then arrange these fingers. Okay, forefinger, center finger, thumb. You have to arrange according to whatever directions are given to you. Now we are not having that, how to apply and all that. So don't bother about it. But that is how it was supposed to be applied. So I'll repeat once again what the rule says. They say that if you stretch your forefinger, center finger and thumb of your left hand such that they are mutually perpendicular to each other. Okay. And now if your forefinger is in the direction of the magnetic field, if your center finger is in the direction of the current, say current is going down, then your thumb, you look at the position of the thumb, it is going for me, it's going from left to right in that direction. So the force is in this direction, like the conductor will move this way. Clear everyone? Yes, we don't have this application, but we'll do one of them. I just want to do it right now, just for you all to understand. So look at the picture which is there on your screen now. So everything we will do with reference to this. So first go to the yo position. Those who want to try, they try it out along with me. Go to yo. Now what do you do? I am turning my hand in such a way that my finger goes from north to south. Okay. You should point from north to south, not south to north. So point your finger north to south like this. But what will you notice, when you keep your finger like this, the thumb must be facing you, right? Towards you. And center finger is going down, meaning current is going down according to your hand. But what is the arrow on the screen, guys? It's going in the upward direction, right? So you will have to turn your hand, guys, this way. So see, those who are yoga students, they have an advantage, guys. They will probably have a better flexibility to do. Or those who've done some, Bharatnatyam and all, probably they will have more flexibility with the hand. So see, this is how we are holding it. Everybody, see, those who are trying, just check once again. Forefinger going from north to south. Center finger is in the upward direction. You can see the black line going upwards. That's a current. And thumb is the direction of the force. Now, tell me, how is the direction of the force for you all, guys? Is it going is it pointing towards the screen or is it pointing towards you?
Towards the screen.
Towards the screen, correct. Even I got that only. But what? Guys, look at this now. But what? If I will reverse the direction of the current, then what would happen? Look at this. If you reverse the direction of the current, then what you have to do, you will have to just turn your hand upside down this way. Now, guys, what will be the force on this conductor? Towards the
Towards
screen
us.
or towards you?
Towards us.
Towards you, yeah, exactly. Same. Yeah, got it. So this is how we used to apply in a motor and all that, like, but then all that is not there now for you all. So do you realize one thing? If you reverse the direction of current, what will happen to the direction of the motion? That will also reverse. Nihar, what if I'm using a very strong magnet? Then what will happen? So what can you say about the deflection?
There will be more deflection.
Exactly, more force or more deflection. If I use a stronger magnet or if I pass more current, same result, more deflection, basically. What if I don't pass any current only? Will the conductor still deflect?
No, it's an electromagnet.
It will not
It's
deflect.
an
Exactly.
electromagnet, so it won't.
Yeah, because if you're not passing current, one more thing, let's not use the word electromagnet for it. Huh? It's not an electromagnet actually. So when you're not passing current, there is no magnetic field around it, and hence there is no deflection. Okay. So guys, these are the few pointers you had to just note. That's all you have in the B part of the chapter. So in B part, guys, you have to learn 10.11. Guys, mark everybody. Learn only 10.11. That too only whatever I have marked. That's all.
So, sir, nothing of the simple DC motor is there.
Nothing. Only 10.11. In that also, I'll tell you one more thing. I forgot to mark one thing, guys. On page 242, you see figure 10.22.
Yes.
I have marked over the JU, right? Just understand. Below that figure, now there are 4 pointers are given, right? Experimentally, it is observed.
Yes.
So there you may mark JR. Like you don't have to by heart it. Just understand those whatever they've given. Like how will the conductor move up, down, or something. So I forgot to write JR over there. You don't need to by heart that also. Clear? So, and guys, everything else is cancelled. I'll tell you which questions are there from the exercise. Go to exercise 10B. You have only from questions 1 to 6. That's all. And that is also the part of the homework, guys, for next class. Only 6 questions are there. Nothing else.
In the exercise.
Yeah. Exercise 10B, question 1 to 6. Example तो एक भी नहीं है, सब cancel है. Because all the questions were on motor. Guys, done? Everybody sorted now with this?
In A part, everything is there.
In A part, everything is there, yeah. I think, yeah, everything we did, yeah. Except electric bell, I think is not there, yeah. Electric bell nahi tha usme. Okay, we'll start C part, guys. Anybody have doubt? Let me know now. Here.
So transformer we don't have, no?
No. I'll give you that also. As we keep doing B part, I'll give you the markings also. C part, sorry. Okay, guys, we'll do one thing. We'll start a new meeting for the C part. So we'll finish everything in that one meeting only in C part also. Guys, C part, actually B part was very little only, not like much, but C part is like the proper application type to understand. Okay, so I'll end this meeting. Everyone please rejoin now.